Hello everyone, I'm Mathieu Gascon, student at the University of Montreal, and I will present you a joint work with Johan Hansen-Metzi from the University of Sherbrooke and Nadia Elmabrook from the University of Montreal on non-binary tree reconciliation with endosymbiotic gene transfer. The results that will be shown in this presentation are the subject of a paper accepted at the Workshop on Algorithms in Bioinformatics 2022. Here, we consider an extension of the gene tree species tree reconciliation model accounting for endosymbiotic gene transfer, or EGT, which is a gene transfer between the mitochondrial and nuclear genome of the same species. Our goal is to understand the concerted evolution of the eukaryotic, mitochondrial, and nuclear genomes. We consider the problem of simultaneously refining and reconciling a multi-bifurcated gene tree, or non-binary tree, under the DLE evolutionary model, where DLE stands for duplication, loss, and EGT events. So in this presentation, I will first introduce the DLE reconciliation model. Then I will present our work on the DLE non-binary reconciliation problem, which is the main problem we studied. I will then talk about a related subproblem, the DLE binary labeling problem. And finally, I will end the presentation with a conclusion. The goal of the DLE reconciliation model is to explain the incongruence between a gene tree and a species tree using 5 evolutionary events. That is, speciation, duplication, loss, endosymbiotic gene transfer, or EGT, and finally, endosymbiotic gene transfer loss, or EGTL. We also consider 2 different labelings of the nodes in the reconciliation. First, a species labeling, and second, a genome labeling, which is a binary labeling indicating whether the gene is located in the mitochondrial genome or in the nuclear genome. I will start by explaining the effect of each considered events. Here we have a species tree S and a reconciliation R, where all nodes of the reconciliation has 2 labels. The letters A, B, and C are the species labels, and the subscript I is the genome binary labeling. And here, a lowercase letter corresponds to the species identified by the same uppercase letter. Here, the node at the root of R is a speciation node, and such, its 2 children must have the species label corresponding to the 2 children in S of the node corresponding to the speciation node. So here, the speciation node has a species label C. So the corresponding node in S is the root, and such, the 2 children of the speciation node must have species label A and B. The 2 children of a speciation node has the same genome binary labeling as their parents. Here we have another reconciliation R, where the root is a duplication node, represented by a rectangle. In case of a duplication node, both the children have the same species label as their parent. So here, as the duplication node at the root of R is labeled by A, both its children are also labeled by A. Once again, for the duplication, the 2 children has the same genome binary labeling as their parent. A loss event represents the loss of a gene copy and is represented in the reconciliation as a gray leaf with a dashed gray line. Here, the root of the reconciliation R is an EGT event, represented by a triangle, which is a transfer from the genome I to the genome 1 minus I of the same species, but also preserving a copy of the gene in the genome I. Finally, here the root of the reconciliation R is a EGTL node, once again represented by a triangle, but this time the node is an unary node, which is a transfer from the genome I to the genome 1 minus I of the same species, followed by a loss of the gene copy in the genome I. Here's an example of the DLE reconciliation problem, where we have on the left the input, that is a species tree S and a gene tree G, whose leaves both have a species label and a genome binary label. And on the right, we have one possible DLE reconciliation of J with S. Here, the internal node species labeling of the reconciliation R corresponds to the LC mapping with S, which is the optimal mapping for the DLE reconciliation. We attribute a cost to each event in DLE, which is the set of the considered events. We assume, as usual, a zero cost for speciations. The cost is said to be unitary when the cost of all the events other than the speciation are equal. The cost of a DLE reconciliation is the sum of costs of the events in the reconciliation. And here we seek a most parsimonious reconciliation. So we say that the DLE reconciliation is optimal if it is of minimum cost. Before defining the DLE non-binary reconciliation problem, I must first introduce the definition of a binary refinement. A binary refinement G' of a non-binary tree G is a binary tree with the same leaf set as G, for which every node of G has a corresponding node in G' with the same clade. Here, the clade of a node is defined by the multi-set of the labels of the leaves below the node. For example, we have on the left a tree G, which is a non-binary tree, and on the right, a possible binary refinement G' of G. Here we considered both the species labeling and the genome binary labeling for the binary refinement, but we can also define a binary refinement in the same way for a tree without a genome binary label. I can now state the DLE non-binary reconciliation problem as follows. Given a binary species tree S, a non-binary gene tree G, and a cost function on the set DLE, find the tree G' over all binary refinement of G, leading to an optimal DLE reconciliation with S, and return the corresponding DLE reconciliation. So for example, here we have on the left the input, which is a species tree S and a non-binary gene tree G. We consider a unitary cost of events. And on the right, we have the corresponding optimal DLE reconciliation of a tree G', which is a binary refinement of G, where here G' is the same as R, but without the leaf in gray and without the events. Our resolution method for this problem operates in two steps. The first step is to find a binary refinement without taking the genome labeling into account, G' of G, leading to an optimal DL reconciliation with S by solving the DL non-binary reconciliation problem, where the DL non-binary reconciliation problem is defined the same way as the DLE non-binary reconciliation problem, ignoring the EGT and EGTL events and the genome binary labeling of nodes. The step 2 is then, given G' obtained at step 1, where here G' doesn't have a genome labeling, find a genome labeling of the nodes of G' such that G' is a binary refinement of G, this time taking into account the genome labeling of G, leading to an optimal DLE reconciliation. The idea here is that we want to first try to minimize the number of duplication and losses, and then from there we want to minimize the number of EGT and EGTL events. So for an example of step 1, we have as input the species tree S and a non-binary gene tree G. We first, we don't care about the genome labeling of G. And then we find a tree G' leading to an optimal DL reconciliation with S. So here on the right, we have the optimal DL reconciliation of a binary refinement G' of G. Once again, G' here is the tree R without the leaf in gray and without the events. Then for step 2, we have in input the tree G' obtained in step 1, and we want to find a genome labeling of the nodes of G' such that G' is a binary refinement of G, leading to an optimal DLE reconciliation. This methodology is a greedy heuristic and it is not guaranteed to be optimal. Step 1 can be solved efficiently using polytomy solver, which is an exact algorithm solving the DL non-binary reconciliation problem. Step 2 is defined as the DLE binary labeling problem, that is the subject of the next section. Before defining the DLE binary labeling problem, I must introduce the definition of a B constraint. For a gene tree G without genome labeling, we define a B constraint M as a set of matrices M of X for X and internal node of G, corresponding to the constraints on the genome labeling of G. More precisely, the matrix Fm of X states the number of occurrences of each possible label, species and genome label, in the leaves under the node X. A tree G prime obtained from G by adding genome labeling to the leaves of G, here we supposed that G doesn't have a genome labeling, is said to be consistent with the B constraint M if it respects all the matrices M of X of M. Here, the B constraint M is induced by the genome binary labeling of the gene tree given in input to the DLE non-binary reconciliation program. For example, we have on the left the input to the DLE non-binary reconciliation problem, and on the right we have a possible binary refinement G prime without a genome binary labeling of its leaves. And we have the B constraint M being the set of those four matrices. If we look at the polytomy on the left of the tree G, we see that the corresponding node in G prime has a matrix that states that we need 2 leaves labeled by B0 under it and 1 leaf labeled by A1 under it, as it is the case in G. Here we added a genome binary labeling to the leaves of G prime, leading to a tree G prime consistent with the B constraint M. I can now state the DLE binary labeling problem as follows. Given a binary tree G without genome labeling, a B constraint M, and a species tree S, find the tree G prime over all tree consistent with the B constraint M, obtained by adding a genome labeling to the leaves of G, leading to an optimal DLE reconciliation with S, and return the corresponding DLE reconciliation. So, for example, we have on the left the input, the species tree S, the gene tree G without genome labeling, and the B constraint M. And on the right, we have the solution to the problem, which is the optimal DLE reconciliation of a tree that is consistent with the B constraint M. Once again, here the tree G prime is the same as the tree R without the leaf in gray and without the events. We proved that the decision version of the DLE binary labeling problem is NP-complete for an arbitrary binary refinement G given in input by reduction from the monotone not all equal tree satisfiability problem. The problem remains NP-complete for unitary cost, even if the B constraint given in input contains only one matrix corresponding to the root of G, and even if each species label is present at most 2 times in the leaves of the gene tree G. A natural heuristic for the DLE binary labeling problem would be to solve each polytomy individually in post-order. In fact, this strategy leads to an exact algorithm for the DL non-binary reconciliation problem. However, in the case of the DLE reconciliation, as the genome labeling of internal nodes introduces a dependency between the polytomies, this heuristic is not exact for an arbitrary cost of operations. We developed a heuristic using that idea and showed that it is in fact exact for a unitary cost of operation. Let the DLE binary labeling root problem, or DLE bin LR problem, be the DLE binary labeling problem where the B constraint given in input contains only one matrix corresponding to the root of G. We considered the restriction of the DLE bin LR problem where genes are specific to a single genome, mitochondrial or nuclear genome, in all but one species that we denote sigma. We can solve this problem by first finding the optimal DL reconciliation and then find the optimal DLE reconciliation by converting some duplication events into EGT events and by adding some EGTL events. This leads to an exact algorithm that runs in O of n times k squared time, where n is the size of G and k is the number of leaves with species labeled sigma that must have genome label 0 according to the B constraints given in input. In conclusion, we explored a 2-steps method for the DLE non-binary reconciliation problem, where the first step is to solve the DL non-binary reconciliation problem, And the second step is to solve the DLE binary labeling problem. We showed that the DLE binary labeling problem is NP-complete. Our heuristic for the DLE binary labeling problem is exact of case in unitary cost of operations. The considered restriction of the DLE bin LR problem, where genes are specific to a single genome in all but one species, can be solved in polynomial time. And we now consider extending polytomy solver to solve the DLE non-binary reconciliation problem directly without relying on a two-steps method. As the complexity of the DLE non-binary reconciliation problem is unknown, it is possible that the polynomial time polytomy solver algorithm could be extended to solve a multi-furcated tree with a genome labeling of leaves, probably at least in special cases. Thank you for listening.